Hello, my name is Joshua Tyler, and today I'm going to talk about something that kind of interests me, and that is theoretical maximums of things, testing the limits. So today I'm going to be talking about the theoretical maximum throughput of fiber. So in the world of telecommunications, there are essentially three ways to send information. Well, I guess four if you want to count smoke signals, but those are a little antiquated. So, in the spirit of not causing climate change, well, too much, there's essentially three ways. There's wireless communication, there's copper communication, and there is fiber communication. And today I'm going to be looking at fiber communication and looking at it versus the copper communication. So the issue with copper communication, well, the way copper communication works is that you have a receiver and you have a digital to analog converter, and the way you send a bit is sending a voltage level. And the issue with sending data through copper over a long distance is that you have to send a large amount of voltage in order to represent a one, and then sometimes it's not very good to send a zero as a one because there's noise that interferes with the total signal. And sometimes when you have a high frequency data transmission, then induce uh, your you induce a higher probability of noise interference. And there's also, with a higher switching frequency, so switching from one state to another, a shorter amount of time to switch from one state to another state. You need more energy to do that. So it's not like you just sending, well, let's say 15 volts, and then whatever capacitance or inductance on the line, you have to fight that. And so switching frequency, it takes quite a bit of energy. And if you go to an analog electronics lab, then you'll see sometimes, they base their spec based on how fast of a voltage switch that you can have. So fiber kind of gets rid of that problem where it just pulses a laser at one end of the fiber, and then because there's less interference due to noise, it can send that light down the fiber using considerably less energy than by using a voltage level versus light being on or off. Now, sometimes it's not very good to have light being off as a zero or light being on, and it's sometimes that you send a zero or a one using a certain modulation scheme instead of just sending a zero or a one. But here we'll just talk about a zero or one. Uh, well, essentially, one level of light is a zero, and then another level of light, typically a greater level of light, is a one. And the reason we don't typically say zero light equals a zero is because there's too much noise. So if we say, oh, if it's under a certain level, then it's or if it's close to zero, then it's one, because there still is electromagnetic radiation that induces noise on the fiber line. It's just greatly reduced because it is light. There's less spectral interference on the frequency band that is light. Um, let's see what else. So less perturbance due to the noise, less energy to send, and then here we're going to see a higher theoretical throughput. So here I'm going to set my sampling frequency. So the light wave that I want to essentially send my information on is going to be at 6 times 10 to the 14. So what is that? Like 600 petahertz. And in order to actually see that maximum theoretical frequency, I'm going to multiply that by 2 for our sampling frequency, and then I'm going to say our time sampling is one, or sampling time. So the distance between the sampled points in time is going to be 1 divided by our sampling frequency. Then I'm going to test out different pulse widths, because I'm going to test out different theoretical throughputs, just sending 0 to 1. So no, intelligent modulation scheme. Just one level is 1, another level is 0. excuse me. And I'm going to create a signal array that is zeros to just a set of zeros that is 1 times 1 to the length of t. So create an array of 1 to the length t of zeros. I'm going to say for I equals 1 to the length of our time array. If t is less than our pulse width, the signal equals 1, else break. That's an optimization, so we only look at t less than our pulse width. Then I'm going to simulate our signal energy. That's not really necessary for the purposes of this. That's just something I personally wanted to see. Then I'm going to create our frequency plot. So when I plot the frequency response, I want it to be from, well, initially negative sampling frequency to positive sampling frequency divided by 2, all on length t. Then I'm going to take the fast Fourier transform, so that is discrete in time, discrete in frequency, divided by the total length of our signal to maximum. That's just the way we do it in MATLAB. And then 6-spec is, so I'm going to normalize it. So our maximum is 1. And then I'm going to, so the way MATLAB works is kind of weird. I'm going to take it from frequency response to 0, so essentially the midpoint upwards, and then I'm going to flip that. So I'm going to cut it in half, look at the second half, and then flip that, and that's going to be our actual single-sided response. And then I'm going to take fplot. Well, then to see the dB loss at its frequency, I'm going to multiply. Well, I'm going to take the log 10 of the absolute value of that signal and multiply it by 10, and then frequency plot greater than 0. So single-sided spectral density response of that signal. And so then I'm going to create a subplot. Then I'm going to say plot it in milliseconds, so our time domain response. And then the second plot will be our frequency response in terms of spectral density, and that will be in megahertz. And that's not really necessary. That's not really necessary either. And then I'm going to say, going to represent our pulse width in terms of picoseconds. Then I will determine our pulses per second by in terms of terapulses. Theoretical throughput is our terapulses divided by 8, and that will give us our terabytes per second. And then, just Netflix streams based on 0.625 megabits per second. Okay, so now let's say a pulse of 1 e negative. Let's just say 1 megapulses per second. So I'm going to plot that and then see that. Yeah, plot that. Give me a second. I got to pull that up on OBS. There we go. So essentially what happens, the relationship between frequency and time is that if you have a shorter response in time, you have a wider response in frequency. So the shorter that you make your pulse, the wider it will be in frequency. So based on the attenuation that happens just due to, physics putting a wall on your frequency response, you can determine how short you can make that pulse. And then how short you can make that pulse determines, your throughput, how many pulses per second, how many bits per second, how many bytes per second. So we can see here our spectral density. So that is the second plot. The first plot is our time response. So that's just looking at a single pulse in time. So that's just a pulse of 1. So then let's see, what do we have? So our 0 dB means a 0 dB loss in for our signal response. And then at -3, that is representative of losing half of our energy. At 6, it's representative of losing 3/4 of our energy, so on and so forth. So we essentially divide by 2 every 3 dB down. So if we're at something like -50, if we see that -50 there on the, let's see, that is my left, sorry, directions. So 50 dB is extremely unlikely. Well, we just don't have energy at those frequencies. So seeing this, we know that our pulses, we know that this pulse we can transmit with this pulse width. And let's see. So let me go down by 100. So shorten our pulse width by 100. Okay, and now we can see, so we've decreased our pulse width, but we still have probably close to 99.99% of our energy still within spec for this pulse width. So what is the throughput on that? So that is 0.1 terapulses, and that looks like 12.5 gigabytes per second, which is quite a bit. Pun intended. So let's decrease that to 12. Let's see. That is. Oh. Okay, so that looks like 12. Times 10 to the negative 12. So that is a 1 picosecond long pulse. So that is 1 terapulses per second. And then that is a throughput of essentially 125 gigabytes per second. And we see here the energy, still predominantly within our signal spec. So that is within spec of sending information at that frequency. So let's reduce it by an order of 100 again. So that is 0.01 picoseconds. That is 100 terapulses. That is 12.5 terabytes per second. And I'm going to have to fix that equation for Netflix streams because that is not right. So if we look here, now we can actually see a little more of the way the frequency response acts. So this is essentially harmonics, if that makes sense. So when you send something at a certain frequency, you actually get resultant harmonics just due to physics. That's just true. So it was a music channel, now it's more of a science / complaining channel or / gaming. Sorry. Deal with it. So anyway, we see these resultant harmonics on the line, but still, if we look at this second harmonic is at kind of the maximum. Look at that. That actually looks like a Poisson distribution. -6. So if we're at 3/4 energy or past losing 75% of our energy there, we are here. What is that? We've lost, we're almost at 1/8 energy here. We lose a large amount of energy, so we're still in spec. So typically what we care about is that first main lobe. So this is a sync function. We care about the first main lobe. The majority of the energy, something like 97% of the actual signal's energy, is contained within that main lobe. So knowing that, I think we can decrease it some more. We're going to go, let's say 5. So we're going to cut it by half. Excuse me. So what is that? 0.005 picoseconds. My Latin doesn't go past pico because I never see past pico in the lab. Pulses per second, 200 terapulses per second, 25 terabits per second. And let me fix that. So we have our terabits per second. Um, let's see if we divide that 1 divided by. Okay, so we can do 40,000 concurrent Netflix streams at 25 terabits per second. So 40,000. I mean, that's not insignificant. Um, so looking at that, well, yeah. So still, oh boy, sorry, I forgot to put that up there. Um, wow, OBS really doesn't like me closing and reopening. Um, but it's free, so can't complain. Okay, so anyway, we see still main lobe is within spec. We have 2 harmonics in there, so that's still good. So let's decrease it by, I don't know, by half again. So 2.5 times 10 to the negative 15, what's that, 2.5 petapulses. So let's see what the result is there. That's 80,000 Netflix streams concurrently. I think that's good. That's assuming 0.625. What is Netflix data rate? Let's see. Low is 3 internet connection speed recommendations. So 25 megabits for 4K, 5 megabits for, let's say 5 megabits. 5 megabits for HD. Okay, so about 10,000 Netflix streams on a single line of fiber. See, the solution that they'll say, so this is single mode fiber. So this is a single strand of fiber that we're sending at. Typically, things will have like there will be multiple strands per line. So let's see. Still main lobe. Oh shoot. Main lobe is within spec. The majority of our power is still in spec. So let's see. So that's 1,000. Um, I think some scientists got 255 pulses per second. So the kind of the issue with you're running into more than one limitation when it gets to this point. So I'm going to go ahead and stop it there because we're starting to lose power that's unable to sample. And keep in mind that frequency response is not ideal. So ideal is a rectangle, but then you know when we see frequency response in the real world, it's low pass, so it actually drops off in dB response. So let's see, pulse width, yeah, so 0.0025 picoseconds, 400 terapulses per second, 50 terabytes per second. Oh, that's megabits. So megabits. So divide by 8. So not multiplying by 8. So that's 80,000 Netflix streams that you can have on a single line of fiber. So that's not insignificant. That's the size of some small cities. So think about it. Scale up your fiber length, and plus 5 megabits isn't the only thing. So if we had, well, let's say Ultra HD, so 16,000. So 16,000 people could watch 4K Netflix theoretically on a single line of fiber, or a single strand of fiber. So let's say how many strands of fiber per line. Each cable can have as few as 2 strands at or as many as several hundred. And keep in mind that this is only transmitting at a single frequency of light. So when you typically, the wonderful thing about fiber is you can actually send multiple multiple forms of light information on a single strand. You can section off these bandwidths of light. So you have what your Roy G. Biv. So you have like your red and your yellow and your blue and your you can section off these bandwidths to send on a single line. So this is just a single. This is just sending information, single color, single strand. So multiply that by however many bandwidths you can section off per line, and then multiply that by how many strands per line that you have, or your bandwidth per strand, and then your strands per strands per line. So let me look width per fiber line. Bandwidth per line. Well, I mean, you can section it off, but I mean, even if you have, so let's say that you have 20 strands in a line, you know, multiply 50 by 20, what is that? A petabyte per second for a single line of fiber. 16,000 times 20. So that's 320,000. So theoretically, and I say theoretically because you run into more issues than one when you redline physics. So you run into things like switching frequency of the fiber modem. So sending the fiber, you know, you have to be able to process that much information at once, and you can see even with like these modern CPUs, we're starting we have with the computational stuff that we have, we still don't have 100 gigabit for a single computer. We have in the data center we have like 100 gigabit cards that we can put in. Um, it's hard to transmit that much data with a single. I mean, even with you know like 12 processing cores. I was actually looking at I built a RAID drive for my computer, 2 terabytes at 14.5 gigabytes per second. When I did, when I hit that thing, when I read at that rate, it hits a 12 core CPU, 24 thread, running at like 4.9 gigahertz, or no, 4.8 gigahertz, because that's just the physics limit of that CPU. Um, it hits it hard. So, being able to process that much data to send per second is a limitation. That's a silicone limit. Well, that's not like physics silicone limitation. That's just a limitation of our current processing technologies to be able to send it that much, and then also receive it, because so you have to demodulate that too. So in order to demodulate that data rate, you're running into a lot of issues, and that doesn't even begin to talk about the different modulation schemes that we have. So sometimes we actually send a whole lot of data, in terms of like a signal or like a symbol, and those symbols will mean a bit. So um, you can actually send a whole lot of data and only get one bit. So there's um, more limit than just the frequency. It's just that if we get our technology to the point where we can utilize fiber to its full extent, we can get up to 50 terabytes for theoretically, we can get up to 50 terabytes per second, which, 50 terabytes per second, that's transferring the contents of like a whole household worth of information in a second, or, less, because some people, you have your 1 terabyte hard drive, you know, you could send that information 50 times in 1 second, which, you know, regular users, we don't even need that. I mean, even Call of Duty Warzone, what is that, like 150, almost 200 gigabytes. Oh, boy, that'll be the day when a game is a couple hundred terabytes. I wouldn't be surprised. But anyway, we the idea that I want to show here is, the shorter that we have it in time, the wider that we have it in frequency, and this is a good way to. This is something that you can do kind of back of the napkin programming. That you can actually see what the theoretical limits are, and you can determine your throughput rates, theoretical throughputs. Anyway, I think that's all I want to say for this video. I will see you again if I do.